Hello. Thank you so much for coming to this collaborative effort between the Cleveland Institute of Music and Case Western Reserve University. We are really happy to have you here. Today's going to be quite a bit different from concerts you've been to before, and I think it's quite exciting. So we're calling this Crystals of Sound. And in this, you're going to see some visualizations on the projector the whole time. So I want to walk you through what you can expect to see and how to interpret it a bit. So what you're going to see is called a tonitz, which stands for tone grouping. And a tonitz is simply a way to organize the 12 chromatic pitches in a way that mimics the relationships of diatonicism. So a quick few notes. As you'll see up here, horizontal lines represent perfect fifths, intervals of 7 half steps. So F to C, C to G, G to D, and on so. The next most important interval we're concerned about is the third, the major and the minor third. These are represented by diagonal lines. F to A, traveling from bottom left to upper right, is a major third. Traveling from upper left to bottom right, E to G is a minor third. And when we complete the triangle, we get our standard major and minor triads. A downward pointing triangle is a minor triad, A minor here, A, C, E. An upward pointing triad is a major triad, G major, G, B, D. But the tonitz doesn't stop there. You can organize entire keys in a beautiful way. For example, here we have C major, and you'll notice the beautiful structure created by it. C, D, E, F, G, A, B. And we can also extend chords beyond standard triads into seventh chords and on so, simply by adding an extra edge to our triangles. Here we have G major, and we're going to add a seventh, F there, and create G dominant 7. And the beauty of the structure of the tonitz is that once you've created a certain structure, whether a triad, a seventh chord, a key, or whatever, if you want to transpose that, all you have to do is move that same structure to wherever you want it. The shape itself doesn't change. So here, G dominant 7, G, B, D, F, becomes C dominant 7, C, E, G, B flat, simply by moving it across the tonitz. So what we're going to see partially here is using statistics to quantify musical ideas, namely Markov processes. So the question we ask is, can we find a way to quantify a composer's style, a piece's harmonic tendency, an entire genre style? And the answer is yes. And it's a very simple idea. A chord by itself is not particularly important and doesn't tell you much. What we're interested in is how do chords move from one to one another. It's like putting a word by itself. A word by itself doesn't mean much, but when you put that word in a sentence, you're given context about the word and meaning. And we're looking to quantify those meanings. So what we do is simply count up how many times one harmony moves to another harmony and divide it by all the possible ways and all the instances that harmonies move between each other. And that gives us an average of different types of harmonic motion, which we can quantify in this table. For example, here, the 1 chord will move to a 4 chord 26% of the time. And we can use this method on any piece, any composer's output, any style, any genre, to quantify the harmonic tendencies of that. And of course, looking at giant tables of numbers isn't particularly informative, so we can use a visual way of looking at it called a heat map, in which the colors simply correspond to how often those different harmonic motions occur, allowing us to quickly and easily visually compare different styles, composers, pieces, etc. Now, the way we actually put this into practice is what's called a random walk, which is when we turn this table loose and allow a computer to make choices about harmonies based on the probabilities we give it. So here you'll see we have the opening of the Brahms Intermezzo in A major, Opus 118, number 2. I'm just going to play these few measures for you. So now what I'm going to do is take, doesn't want to let me talk. Now what I'm going to do is take a Markov table for this Brahms piece and allow it to mimic the Brahms piece by making similar harmonic choices to what Brahms did. And the beauty of this process is, because it's entirely random, if you don't like what you get, run the process again, and you'll get something new every single time, just as you're going to get today. Furthermore, the neat thing about this math is, even though I've been talking about diatonic processes so far, major and minor keys, major and minor chords, the math doesn't know what diatonicism is. It doesn't care. You can use any collections as your quote-unquote harmonies. So here I've taken entirely non-diatonic pitch sets, and I'm going to use them to create something that sounds very unlike what we've heard before, but still follows the same process. And now I'm going to turn it over to my colleague, Jesse Berezovsky, who's going to tell you more.
Thank you. So we just heard about a lot of the patterns that emerge in music, that appear in musical harmony. And you can ask similar questions about how what patterns exist in the musical rhythm as well. But what I want to talk about is, why do those patterns emerge? Is it just an arbitrary choice by the composer, or is there some fundamental reason why, across so much time and across so many different cultures, there are so many commonalities in how people compose music? And so to do that, we draw from techniques from physics, specifically techniques that we use to understand transitions between the phases of matter, from, say, solid to liquid to gas. And in a nutshell, the reason why order emerges in physical systems is because of a trade-off between the tendency of a system to want to lower its energy, but that tendency is in a tension with a different tendency, which is the desire of a system to raise its entropy, or its amount of disorder. Usually low energy states are ordered and regular, but there has to be a balance between these two factors. And in a physical system, the one that wins is set by the temperature. So the temperature is, you could define it, in fact, as how much increase in energy you're willing to trade for an increase in entropy. And so at different temperatures, different balances are struck, say leading at high temperatures to the disordered phase of water vapor, and then as you cool it down, you get the sort of regular, ordered, beautiful structures of crystals. We can apply the same ideas to understand how order emerges in music. Instead of a balance between energy and entropy, though, music has different tensions. For example, there are certain things that we find psychologically pleasing. Certain combinations of pitches sound more consonant, and others sound more dissonant. We like to hear repeated patterns in music. But at the same time, we don't want to take either of these to too much of an extreme, where the music will become boring and inexpressive, and composers won't be able to write the music they want to write, listeners will be bored. And so we need complexity, we need variation as well. And so these two are often in a conflict with each other, in a tension. And so we can think about this in the same way and resolve that tension by setting a balance set by a parameter which we could call temperature. In other words, how much decrease in consonance or decrease in repetition you're willing to trade for an increase in complexity. And that balance might be different from person to person or from culture to culture, but some sort of balance can be struck. So I'll give you some examples now. If we put these ideas into mathematics, quantify these things, we can use all the tools from physics that we use to understand how phase transitions occur, to understand how order emerges in music. And so I'll show you some results here. So this is showing how rhythm emerges in music. And we start out at high temperature, where we'll hear really a random arrhythmic series of clicks with no particular length of note present. And if you wait as the temperature lowers, you'll see when order emerges, more familiar rhythms come about. So you'll notice as we go to lower temperature, we start to approach a perfectly repetitive pattern, but lose any kind of variation or complexity. We can do a similar thing with musical harmony. We prefer to hear certain combinations of pitches rather than others. And we can simulate this in this cube here, where each dot represents a tone with its pitch labeled by its color. And we start out at high temperature, where within 1 octave shown here, there's no particular pitches present. Any frequency is allowed, which is shown here. As you go around 1 octave, there's notes at every frequency. This just zooms in on 4 particular tones in this lattice. And what I'm going to do is we'll start lowering the temperature, and we'll listen to the sound of these 8 tones and see how the distribution of pitches changes as the temperature decreases. So in that example, we could hear the emergence of harmony as we go from the high temperature random noise to a low temperature harmonic combinations of pitches. And you also note that now we have this sort of a patchwork of different colors, which correspond to a patchwork of different pitches. And if in this distribution here, if you count them, you'll see that there are 12 distinct pitches, just as we use in Western music. If we look closer, we see additional similarities to the harmony of Western music. This again is the tonettes here. This is a slice from that simulation I just showed you. I've labeled the different pitches with our standard notation now. And we see that neighboring regions of different pitches are also the neighboring regions on the tonettes. The ones I've highlighted here, you'll also notice, are the notes of, say, a C major scale. And so notes of a diatonic scale happen to be near each other in this space. And if we look at places where 3 or more of these different regions come together, we get chords. So the one highlighted by this triangle here is a C major chord. Nearby it, we have an E minor chord. And we get other chords as well that emerge from this that are less commonly used in Western music. But together, the rhythm and harmony that we see emerging here give us a way to understand music and also to compose new rhythms and harmonies. Where we look at the placement of the chords on this lattice, we can get rid of the pitches and just see where are those chords occurring, where are 3 or more of these domains coming together. And we get this branching network of strings, I call tonal strings. And actually this mimics something that we see in physics when phase transitions occur. For example, a phase transition hypothesized to have occurred in the very early universe right after the Big Bang is predicted to form these so-called cosmic strings that may still thread through the universe today. So these tonal strings represent chords, and if we move along a path along these strings, that gives us a chord progression. And so here's a close-up of these tonal strings again, labeled by what kind, color-coded by what kind of chords they are. And by moving along a path, just as we saw before, you can have a random walk through the Markov process. Here we can have a random walk along these strings, which generates a chord progression, shown here by this moving black dot. Oops. Let me bring that. Sorry. A little recap.
We knew you wanted encore.
All right. So now I'll turn it back over to hear more about what we are going to be doing today.
So before we talk about what you're going to hear today, I want to talk a little bit about the philosophy and the aim of this project. What we're doing here isn't attempting to replace the human element of music. That's always going to be the most fundamental part of music. Rather, what we're trying to do is uncover the deeper connections between these elements and why humans choose to do what they do with music. So we want to uncover and codify these parallels between physical systems and musical symptoms, not to bypass the human performer or composer. And we're going to explore the human-computer connection and how deeper understanding can enable new creative explorations or create new tools for the learning of music or the experience of music. So today's going to be an exploration of those relationships. You will hear entirely computer-generated pieces. You'll hear pieces that are generated in real time and performed by human musicians. You hear pieces that are composed by a human and also accompanied by a computer in real time. And the most exciting part is at the very end, you will get to be a part of the pieces. You are welcome to come on stage for the last piece and control the system yourself and play in an ensemble. And I strongly encourage you to come on stage and play because it's a lot of fun.
And lastly, before we get started, we'd just like to thank various people that were instrumental in making this performance a reality. There were the students that have worked with me over the last few years developing the theories and the code and the electronics for these systems. Hui Din and Ryan Buckley and Luke Edelman. Thank you. Yeah, all right, thank you. And I'd also like to thank Dean Joy Ward of the College of Arts and Sciences at Case Western Reserve University for funding this project through her Expanding Horizons initiative, which allowed us to really make this a reality. So thank you for that.